video, we are going to continue in the partial fractions section of the book. We are looking at a substitution, a U substitution called a rationalizing substitution, and these often result in partial fractions. So it's actually a combination of two methods, U substitution plus partial fractions. So with rationalizing substitutions, we have a root or more than one root in the expression for the integral. And it's not of the form x squared minus a squared or a squared minus x squared. It's not a trig substitution. So here we see this root x minus 1, but the x is not squared. So that's a clue that you want to use a rationalizing U substitution. So in this case, we're going to let u equal the square root of x minus 1, because that's our troublemaker. We don't know what to do with that. Don't know how to integrate this by any other method. And then we have to find dx here, so I'm going to square both sides to get rid of that square root. So u squared is x minus 1. And then bring the negative 1 over, so u squared plus 1 is equal to x. And now we take the differential of both sides. So on this left-hand side, we get 2u du. And on the right-hand side, we just get 1 dx. So now we start changing this integral over. So on the top, that root x minus 1, that is our u. On the bottom here, we've got 3 times x. Let's take that 3 and bring it on the outside here. So we factor out a 1/3. Now we've got x on the bottom. X here is the same as u squared plus 1. So u squared plus 1. And then don't forget our dx out on the end. That is 2u du. So by that rationalizing U substitution, no more roots here. Let's bring the 2 on the outside here. So we'll now have a 2/3. And let's combine what's left. U times u squared on the top. And then on the bottom, u squared plus 1. So we can't use another U substitution on this because the derivative of the bottom there is 2u, and we've got the u squared, actually du. So what you want to do for this, since these are polynomials, is long division. We want to do partial fractions. So we're going to take that u squared plus 1, and we're going to divide it into the u squared. And there's no u term, so we're going to add a placeholder plus 0u. And then plus 0 on the end. So you divide this u squared by this one. So u squared divided by u squared. Divide the leading terms, and we get 1. So that 1's going to go here. Multiply out in front. So 1 times u squared plus 1 is u squared plus 1. And then we're going to subtract. So u squared minus u squared, 0. So those guys cancel out. 0. Minus 1 is negative 1. So we've got a remainder of negative 1, which we put over the divisor. So this is minus 1 over u squared plus 1. So now we'll trade this guy out for what we got in the long division. So we'll have a 2/3 out in front. And now we're integrating 1 minus 1 over u squared plus 1. du. So now we can integrate this. So we got our 2/3 out in front. Antiderivative of 1 is u minus antiderivative 1 over u squared plus 1. Do you recognize that one? It's inverse tangent. So this will be inverse tangent of u. And then plus our constant on the end because it's an indefinite integral. And now we just have to use our original substitution to change back to x's. So this is 2/3. And then we've got u, which is root x minus 1, minus inverse tangent of u, which is root x minus 1, and plus c. And we got it. So this one, we actually didn't have to do the partial fractions on this part because it ended up being inverse tangent. We only had to do the long division. So sometimes you have to do the long division and then you have to do partial fractions on your quotient that results. Sometimes you just have to do the partial fractions. So let's look at another example here of rationalizing substitutions. So in example number 5, we've got x to the 1/2 power, which is really square root of x. So this is actually the same as the integral of, we've got square root x on top, and on the bottom 1 plus, and x to the 1/3 is cube root of x dx. So if you get roots here, change them to fractional powers. And then for our substitution here, this one is a little bit different. We're going to use a rationalizing U substitution. U is going to be, and you use the LCD of 1/2 and 1/3, which is 1/6. So this is going to be x to the 1/6 power. And again, this is x to the LCD of all the powers, however many you got. So now that lets us replace these guys if we solve for x here. So take 6 powers on both sides. U to the 6th is going to equal x. So now for this x, we can put in u to the 6th. So this will be integral. On the top, we've got u to the 6th. For our x, that gets a 1/2 power. On the bottom, we've got 1 plus x to the 1/3, so x is u to the 6th. That gets a 1/3 power. And then we've got to take up the dx. So differentiate both sides of this. So the differential of the left-hand side is 6u to the 5th du, and differential of the right-hand side is dx. So out here on the end, we've got a dx, which is 6u to the 5th du. So now let's go ahead and simplify. So this is going to be integral, power to a power, you multiply here. 1/2 of 6 is 3, so that's a u cubed. And then on the bottom, u to the 6th to the 1/3, power to a power, you multiply. 1/3 of 6 is 2, so this is 1 plus u squared. And then times our 6u to the 5th du out on the end. And now you see why I picked the LCD. So I picked the LCD here as the exponent because then that made both of these exponents, when you multiply, turn out to be whole numbers, and now we can do long division. So let's first take our 6 and pull it out in front. And so we'll have 6 times the integral. U cubed times u to the 5th is u to the 8th. And then we are dividing by 1 plus u squared du. Power on the top is bigger than the power on the bottom, so we need to do long division. So we've got u squared plus 1. That is going to divide into u to the 8th. Now, we don't have any other terms, so we'll have to put in some placeholder terms here. Now, the difference in these terms is 2 in the exponent, so you don't have a u term here. So actually, the next term here is not going to be u to the 7th, but u to the 6th. So I'm going to add a plus 0 u to the 6th. And so now we divide our leading coefficients. So u to the 8th divide by u squared. When you divide, you subtract exponents. 8 minus 2 is 6. So that u to the 6th goes right here. We multiply by what's out in front, put it underneath here, and then subtract. So let me move this guy over. Come on. There we go. So u to the 6th times u squared is u to the 8th. U to the 6th times 1 is u to the 6th. And we want to subtract those guys. So we're going to change the signs, minus, minus, and add. So these guys cancel out. 0, u to the 6th minus u to the 6th is negative u to the 6th. Now we divide this coefficient by the u squared. So negative u to the 6th divided by u squared is negative u to the 4th. So that's going to be our next term, minus u to the 4th. So down here, we're going to have to add a plus 0 u to the 4th term placeholder. Or I'm sorry, not there. Next line down. Right there. And now we want to go ahead and multiply our negative u to the 4th by what's out in front, put it under here and subtract. So negative u to the 4th times u squared is negative u to the 6th. Negative u to the 4th times 1, negative u to the 4th. And we want to subtract those guys. So let's change the signs and add. So these guys cancel. 0 u to the 4th plus u to the 4th is u to the 4th. Now divide the leading coefficients again. So u to the 4th divided by u squared. Is u squared. And that goes out here, plus u squared. U squared times what's out in front, and put it underneath and subtract. So u squared times u squared is u to the 4th. U squared times 1 is u squared. We're going to need a placeholder plus 0 u squared up here. And we want to subtract those guys. So let's change the signs here and add. So these guys cancel out. 0 minus 1, negative u squared. We're almost there. Divide the negative u squared by u squared. Negative 1. And that's going to be our last term here. Negative 1 times what's out in front will be negative u squared minus 1. And we need a placeholder 0 here. We want to subtract those guys. So change the signs and add. These guys cancel. 0 and 1 is 1. So there's our remainder of 1, which we put over the divisor. So plus remainder 1 over divisor u squared plus 1. So this thing we're going to trade out for this guy. Okay, so now in our next step, we've got 6 out in front, and we are now integrating u to the 6th minus u to the 4th plus u squared minus 1 plus 1 over u squared plus 1 du. So now we can actually integrate here. So let me move my division out of the way here so we've got a little bit more room. Okay, so now we can integrate. So we got a 6 out in front. This will be u to the 7th divided by 7 minus u to the 5th divided by 5. So it's just power rule. Increase the exponent, divide by the new exponent, plus u cubed over 3 minus antiderivative 1 is u. And then there's that 1 over u squared plus 1 again. That's inverse tangent. So inverse tangent u, and then plus a constant. And now all we got to do is plug back in for our u. X is x to the 1/6 power. So equals, so we got a 6, and then this will be x to the 1/6 to the 7th over 7 minus x to the 1/6 to the 5th divide by 5 plus x to the 1/6 cubed over 3 minus x to the 1/6, and then inverse tan of x to the 1/6. So plus inverse tan x to the 1/6, close up our parentheses, plus c. And then if we want to here, we can do a little bit of this simplifying. Right, power to a power, you multiply exponents. So that's going to be x to the 7/6 power divided by 7 minus, again, power to a power multiply. 5 times 1/6 is 5/6. So x to the 5/6 divided by 5 plus x to the 3/6. 3/6 is 1/2. So it's going to be x to the 1/2 divided by 3 and minus x to the 1/6. And we've got our inverse tangent on the end of x to the 1/6 and plus c, and we got it. Voila. So there again, we didn't have to do partial fractions on this last piece. It just ended up being inverse tangent. And that's pretty common. Sometimes you have to still do your partial fractions on the end, but most of the time it's just long division. And that actually wraps up 7.4, section 7.4. So you are going to try 7.4 for Monday questions and do Tuesday. And there is web work for that also, so there should be web work for most sections going forward, except sometimes before tests I'll omit the web work to make it easier for you. So now we've got a lot of methods under our belt. So let me just kind of give you a little bit of preview here. In section 7.5, we are just going to do some more practice combining all of our methods. So mainly we've been using one method at a time. In section 7.5, we'll actually be starting to use two methods at a time. So I'm just going to give you a bunch of problems on the next exam, and I say, here, integrate this, integrate this, integrate this, and you have to decide which method and how do I attack this problem. Well, here's a strategy to help you out. So number one, simplify your integrand or change its form. So change its form, maybe you have to complete the square, multiply by 1, add 0, get a common denominator, things like that. Number two, always look for a U substitution first. That's the first method we learned of integration after, power rule and stuff like that. So check for a U substitution first. Don't try integration by parts and trig substitutions and, rationalizing all the other stuff if a simple U substitution is going to work. If a U substitution doesn't work, try to classify your integrand. So, what type of an integral is it? Well, if it's a product of a polynomial or a power times e to the x or cosine x, like x e to the x or x squared cosine x or, times a log function, x cubed log x, all those are signals for integration by parts. Okay, so this is, x e to the x, x squared, ln x, all those things that are power or a polynomial times a transcendental function, x cubed cosh x, things like that. That's integration by parts. If it's a rational function, polynomial divide by polynomial, that's what we just did. That's partial fractions. So you recognize that. If it's products of sines and cosines or tangents and secants, then it's a trig integral, which is a different type of U substitution. If it's got a difference or a sum of perfect squares in there underneath the square root, that's your signal for trig substitution. But try everything else first, because trig substitutions are probably the most work. And then if it contains a root, could be a square root or cube root or fourth root or more than one root, but it's not a difference or sum of squares underneath there, then try a rationalizing substitution. So generally you'll let U equal the whole, the expression under the root, including the root, or you'll let U be the LCD of the roots if there's more than one root. And then lastly, you might have to use more than one method. So let's look at an example here to start off. And actually this section, I'm going to give you a bunch of examples, but then we're going to spend quite a bit of time in class, practicing all of our methods, doing some group work in class. So what if we wanted to integrate 3 to the 2x plus 3 to the x power dx? Well, it's an exponential and it's a function power up here. So I'm looking at this, I'm like, well, can we use a U substitution? Well, not really like it is, but notice here, if we break this apart, you know, when you add the exponents, that comes from multiplying. So we can break this apart and say, well, this is 3 to the 2x power. Let's see, times 3 to the x power dx. And then 3 to the 2x, that's a multiplication in the exponent. So I can actually write that as 3 to the x quantity squared times 3 to the x dx. Oh, I'm sorry, 3 to the 3 to the x. The exponent is 3 to the x. So I'm looking at this and I'm like, the derivative of 3 to the x is 3 to the x, and I've got two 3 to the x's down there. If I did a u substitution and let u equal 3 to the x, then I'd have, you know, down here, one of these 3 to the x's would be my du, or most of my du, and the other 3 to the x would be u. And that would simplify this integral a lot. So let's try to use a u substitution here. So let's use u equals 3 to the x, and then du is going to equal 3 to the x, and then since it's a different base than base e, it's times ln 3. So let's see here. I don't have the ln 3 in here, but I could multiply and divide by log of 3, right? So I could multiply by ln of 3 right here, and then compensate on the outside, 1 over ln 3. That way I haven't changed the value of the expression. So now I've got a 1 over ln 3 integral. So 3 to the x ln 3. So this ln 3 and one of these 3 to the x's is going to be my du. So what's going to be left over is one of the 3 to the x's and then this 3 to the x. So actually I could do this. I could take that 3 to the x squared. That's 2 copies of 3 to the x. So I could just write that as 3 to the x times 3 to the x, right? So here, these two guys, that's my du. And then this will be u and u. And then I'll have u 3 to the u, which looks like this. That's going to be integration by parts. So we're going to have to specify u and dv. So since we're going to have to use u and dv, looks like it's a two-method problem. Let's change our variable. Let's call our u substitution variable w, and then this will be dw. So this is w, w, dw. Okay. So here, this 3 to the x ln 3, that's our dw, and then this will be w 3 to the w. So w 3 to the w. So that simplified it a lot. So algebra and u substitution. And now we look at this and go, oh, integration by parts. Okay, so our u is going to be the variable part, the w, and our dv is going to be the exponential, 3 to the w. So differentiate here, du is dw. Integrate here. So v is going to be, when you integrate, you get 3 to the w, and you divide by log of the base, ln 3. Because when you differentiate, you multiply by log of the base. So now we want to do uv minus integral v du. So w 3 to the w over log 3. W 3 to the w over log 3. And then minus integral of the bottom row, which is just 3 to the w over log 3 dw. So 3 to the w over ln 3 dw. So now we just have to evaluate this integral. Well, the ln 3 can go out in front, and then we're just integrating 3 to the w. Oh, that's what we did here. We get 3 to the w over log 3. So this is going to equal, I'm going to bring that log 3 out in front. So I've got a 1 over ln 3. And then we've got 3 to the W, 3 to the W. And then minus, this ln3 goes out in front, 1 over ln3. And then integral 3 to the W is 3 to the W over ln3. And now we've integrated everything, plus C. So now we just have to put back in our W here is 3 to the X. So this will be 1 over ln3. And then that W is 3 to the X times 3 to the W power. So 3 to the power 3 to the X minus, we've got 2 ln3s in the denominator there. So I can do 1 over ln of 3 quantity squared. And then I've got, these guys will be out in front, 3 to the W. So times 3 to the W is 3 to the X. And plus C. And we reversed our substitution. We got it. We're done. All right, let's call that good enough. I'll do a bunch more examples on Monday, and then we'll be doing some group work here on Tuesday and probably Wednesday too. Well, enjoy the rest of your break.